Hi, and welcome to the quick video that accompanies the handout on parallel and radial line developments. During the first year, you made a number of transitions. Each one of those was like a piece of card or cards that were taped together. This whole subject basically shows you how we would roll or fold out a sectional view that we could, in fact, cut on the plasma cutter. Now, any shape, like this rectangular box section, could be viewed from one end, and you would get the end view, view from the side, you will get the top view, and the pictorial view. If we now just open this thing out, so let's drop the sides, and then unfold the back, would give us a flat pattern that we could in fact cut out, fold, and then stick back together. Now with the top, the front, we need those two views to be able to develop that out. We could roll this, as you can see by the blue flashing sections, across the screen, and you may add or not bother to add the top section and the bottom section you'll see flashing in magenta. Now the whole idea of this is basically the outside shape is developed from the orthogonal front view and the orthogonal top view. In most of our developments, including this one you see on the screen right now, we would need both views to make an effective model. Now we got the height and we know the side length, so we can unfold this particular type of model. The height is developed directly onto the vertical plane, that's the VP that's marked there. And if we slice it, you can see that it will alter the VP. It will alter it because we are now reducing the height even though the original part is still there. Once we've done that, we can fold it out. But how do we get there? Well, we have given corners on a hexagon, and you can see that we can develop those corners upwards. The frustum is placed on between M and N, which is normal, and the center point is identified. Once we've done that, we can see what the various parts as we step through the line that we can just unfurl from the bottom, which is 6 times 60 between points A and A. That's called the stretch out line. That's just the developed length between A and A. So we can take that 60 and add 60 every time, getting to a total of 6 times 60, which equals 360 millimeters. Now the height on the blank we would need to move across. So we take the true height of the blank piece before we section it, and then we put the height on. So again, it's A to A. Each one of the 60 millimeter sections could be identified on the bottom line, and we can use the offset command to do this from the left hand line. Once we've done that, we develop across from every point along the frustum. 1 goes across, 2 and 6, 3 and 5, and number 4. From that, we can find the intersection between the letters and the numbers, and that will give us the line that goes between 1 to 2, 3 to 4, 4 to 5, 5 to 6, etc. back to 1. That makes our pattern, which we can then kink and fold, and it would make the shape of the 3D object instead of the 2D representations. Now on top of that, sometimes we don't want to just do a frustum. We want to drill a hole or make a piece that will go around a circular component like a piece of tube. And you can see on there that it's a very similar process. We take the component, in this case I think it's 140 millimeters in height. We develop that across, and we're looking at a shape which we've always put the base dimension down, and like some of the examples in the handout, they are numbered, and you'll see later on we will letter them as well. Now once we put the hole in the correct position, you can see that we would have those two sides of the hole that would actually go between A and B and C and D. Now the hole itself is 45 millimeters, and that's in the radius. We would need to divide that up, so we're going to divide it into 8 in this case, and then develop down each of the lines, and the two important ones are the position 1 and 5, and where they would intersect it would give us P, Q, R and S on the pattern. Now the pattern is developed the same as before. We just put the height of the object on there because it is a hole that we're looking at this time, or in this case two holes. We develop both the left and right side out. We just move up from the bottom 140 and then develop, once we've taken a measurement of 60, each of the 6 sections or 5 dividing lines. Now we put the front and the back on there, the M and the N, like they were before, and we put a P section on there. That is the length between A and P where the hole would actually start. We repeat this process for the Q, the R and the S, and then develop across from the lines on the circle. Now once we've done that, the point of intersection between those lines can now be mapped out, and we can draw our shapes, so that once we actually finish with this shape, we have two holes that, once bent around back into the hexagon, would form a hole coming from the front and dropping through the back. Now this, because all the lines are parallel, is the parallel line method. So the parallel line is differentiated by the radial line, and the differences are pretty simple. Any line on these shapes will be parallel to each other, any development line, whether it be a round cylinder or a prismatic or a cubed object. Now when we look at the radial line method, we're looking at something that comes to a point or an apex. That includes squared and segmental pyramids and cones. Now the parallel line method, and if we've got a square-sided object, can be folded out. So we call this unfolding. When we have a round or cylindrical object of any kind, be it conical or flat, we refer to this as rolling out, and that's something we will cover later. Now the object on the screen you can see is a pyramid. Now it doesn't have to be a pyramid. Imagine we had a circle on the base. If we had a circle on the base, it wouldn't be as squared as that pyramid, but we're going to have to divide the circle up into parts, so it will look a little bit flat on each of the edges. This is a typical example. Now every time that we have to develop one of these, there are a number of ways of doing it. You can see by the number flashing on the screen that this is 113.85 degrees. Now we get that by looking at the radius, dividing the true slant length, and then timesing it by 360. Now as far as doing a frustum, the same as we did on the hexagonal component, all we would need would be the center point of the frustum, which we can identify, and the angle at which the thing is to be sliced. But looking at it practically, it's a very similar thing to the hexagonal. Now you can see that we have to divide the bottom circle up into a number of parts. In this case, it's 12. And each one of those will develop up to the top cone. Now if we just fade out the top cone for a second and concentrate on the points around the circle, you can see that we will develop these things up to the baseline of where the cone will be, and we can number them. From there, we develop the lines up to the apex. Whether it's there or not, there is a development apex on there. And again, we look at the frustum line between M and N as a 30-degree line, which we can then look at where the lines on the development go up, and then number them if we want to keep track. You will find that in your handout. Now the way that we figure out the true length is pretty simple, and I'll explain that more in class, but the mathematical formulas for doing it are actually on the screen. Now if you take the angle, and that's the angle of what that will be developed, you're basically going to work out the hypotenuse. And by that, once you take that first number, you can actually develop everything from the 1 to 2, 3, 4, 5, 6, etc. across to the side to make them all true lengths. Now, if we take a pair of dividers and measure the side length, we can actually give a point on the paper and then draw an arc. We can then make sure using a protractor that this is 113.85 degrees. Now the distance of any one of those segments can be measured directly off the circle and then stepped around to fill up that 12 section piece. Now even though it's round, and you can see it's supposed to be round, the number of divisions that you get will differ. If you want a finer finish, we go for a higher number of divisions. And you can see that the protractors on the screen is now measuring each of those side measurements, not down the lines individually, and then forming what would be our radial line development. Okay, so that's enough to go with the handout, and I'll see you all in exercise or lesson 1.